Welcome to Physics 1405. Can you hear me?
Yes, ma'am.
All right, great. Seems to be working now. We can hope. I'm going to go ahead and start the whiteboard so we can work on that. And do you want to tell me about any questions you might have?
I haven't gotten that far reading yet. Let's see. Honestly, the way you set up like the theories and everything, I feel like I understand it pretty well and then just work my way through the labs.
Okay.
And yeah, little by little, I just learn more and then yeah.
Well, that's good. Do you have any confusing topics on the last lab?
On the bungee,
Yeah,
no, the
or
horse.
any previous labs, really, but that one is one that seemed particularly difficult for students generally.
Okay, let me pull that up real quick. I did have a couple in mind I thought of. Hmm. I feel like I did pretty good on that lab.
Mhm.
Um, at first, okay, so when I, okay, I guess it was number 7 on the horsepower.
Okay.
Um,
Do you want to read the question?
sure, it says calculate your power P when taking one step at a time. It gives you the equation, which is really nice. And then it says for the time, use the average of the times recorded for this trip. Then convert your power into units of horsepower using 1 HP equals 746 watts. Record both values below. And so I found the watts by, let me see, power to use horsepower. So oh, wait. Okay, anyway, I got 186 watts. And then when I think I divided horsepower. Yeah, so, okay, let me get my calculator. So the first time I had gotten my horsepower, it was 0.25. And I don't know why I thought that was wrong. So I switched my division. I think I did 746 divided by the other number.
Hmm.
That makes sense. I wish I had all my work in front of me.
Okay. Well, we can talk about unit conversions a little bit. I am having a hard time with this whiteboard though, so
Hmm.
I might I might just pull up a paint document or something that we can use for working.
Okay.
Okay. All right.
But okay, so when I got the 0.25 for my horsepower,
Mhm.
I didn't think it was gonna be so low. I guess I kind of did, but it just didn't look right. So I switched like my numbers when I was dividing, and so I got like let's just say like a 2.7 or something instead. And I was like, you know what, that's definitely not right.
Okay. Well, let's talk. I'll just do a little. Are you still there?
Hmm.
Okay. For some reason, my computer is giving me a message that Zoom quit. Can you see the whiteboard with the message?
Hmm.
Okay. All right. Well, despite the odd technical difficulties, it seems to be working. So, um, let's just assume that you did the calculation correctly. What did you get for watts? Do you remember? Or just throw out a number that we can use for our.
I think it said 186.
Okay. So, if we have 186 watts. Now, the easiest way that I've seen to understand when you're going to do a unit conversion is if you hark back to math class, we all should have had a little bit of math. There's a rule that says if you multiply anything by 1, you get the same thing back. right?
Right. Mm-hmm.
So we have that 1 horsepower is equal to 745.7. I think they give 746 in the lab, right?
Yes, ma'am.
All right, so if we use this equation right here, and we know that we started off with watts and we want to end up with horsepower, what we do is we use this equation to find something that equals 1, that when we times it by this number that we have, including the units, it will change the units. That means that we want a fraction with watts on the bottom. So the way that we would do this is if we divide both sides of this equation by 746 watts, 746 watts over here also, then this divided by this thing equals 1, right? And so it's this fraction over here is a horsepower over 746 watts. So this looks funky. It's got units on top and bottom, but we know by this little algebra that we did that it's equal to 1. So this is called a conversion factor. So if we want to convert the number that you started off with to horsepower, we just multiply it by this version of 1 right here. So the secret to getting anything, to changing the units of it, is finding the special version of 1 that you need, that if you multiply it, it will make the units drop out that you don't want, and it will give you the units that you do. So let's rewrite this up here.
Oh, okay. I was wondering if you were writing on that already because I couldn't see it.
Oh, so can you can't see anything right now?
No, I see the whiteboard, but there's nothing on it.
Oh dear. Here, let me reshare. That might have been.
Okay, I
I'm
see
going to
those.
stop the screen share and then restart it and see if we can get. So what do you see right now?
Just me and you.
Okay. So share screen. We want this one. Okay. So can you see something with writing on it now?
Yes.
Okay, great. All right. So I think my Zoom is threatening me again. Can you see a window popping up in front of this?
No.
Okay, this is really weird because Zoom's crashed twice on me in this one call. Anyhow, you can see on the right-hand side, we have an equation at the top, 1 horsepower equals 746 watts, right? We divided both sides of that equation by 746 watts, and so we ended up with a fraction on one side, 1 horsepower over 746 watts, is equal to the number 1 with no units. So that's what I was talking about when I said that's our conversion factor. Does all that make sense?
Yes.
Okay, great. Now, okay, yeah, apparently my pencil's working. It wasn't a minute ago. Pardon, I've never seen technical difficulties quite this bad on a regular Zoom call like this.
Oh.
But we start off with our 186 watts and we multiply it by 1. And we know from algebra class that if we do that, whatever we get out, even though it might look funky, we know that it's still the same, whatever this was. So if we had something, it was 186 watts of energy, we want it to look different with a different unit, but it's still the same thing. So if we multiply this, our watts are going to cancel out, right? We've got watts on top and watts on bottom. So we end up with the number 186 over 746, and horsepowers is our unit. And units work just like algebraic variables. If you have it multiplied there, or if you just have a unit of watts, it works the same. Okay, so does that make sense?
Yes, so then you would divide the 186 divided by 746, and that would be your horsepower?
Yes, and that does come out to about 2.5, which is what you
Okay,
said, right? And we would
perfect.
take the 0.249 because we're looking, all of these things, all these numbers that we have 3 significant digits. There's 3 numbers there, three place values. And so we would take the 0.249 would be the appropriate number to report.
Oh, I rounded that 9, so I put 0.25.
Okay. Yeah, I usually don't zap people too much, but as like just part of lab teaching, Because when you are in algebra class, if the teacher sees you and sees, oh, she got 0.25, I know the answer is 0.249, algebra teacher knows that you did it perfectly, right?
Okay.
But here in lab class, these three numbers all mean something. It means
Okay.
that you measured it to this accuracy right here. And so it's a little different in labs than it is in algebra class because the number of digits that you choose to round off to actually has an additional scientific meaning of I measured it to 3 digits of accuracy,
Okay.
which that's actually a really good principle. People have been struggling with that and I've been trying to mention it. But sometimes it's a little tricky to explain just, writing in a few sentences. So
Hmm.
that's a great principle.
So I know that lab was due Monday.
Mm-hmm.
Can I fix that?
I'm afraid not. The due dates and we just kind of have to follow the rules in the syllabus. There isn't late work or anything like that. But these same principles of unit conversion and reporting the proper sig figs and everything, those keep coming up in lab. So that's something that you've learned that you will be able to do that much better on like all the rest of the labs.
Okay.
And then also the kind of I do encourage a logic check, and I will double check. Usually I kind of post a document of kind of like a checklist what you do, and when once you have an answer and you've checked the units and everything makes sense, you can go back and say, hey, does this logically make sense?
Hmm.
And given that horsepowers originally were the rate of work that a horse could do, like literally when that was their means of plowing a field or something, that was supposed to be a measure of the amount of effort that a horse could like sustainably put out, and that kind of
Hmm.
worker horse. So given that human beings were a little bit smaller, maybe we can not put out quite as much energy. Would it make sense that you can put out about a quarter of the energy that a working horse could?
Right.
So that's kind of the logic check at the end. If you're like, oh, that doesn't look right, it's always good to kind of see if we can come up with something to like some fact to tie it in to see does the number are we comfortable with it? Is it about the right size or not?
Hmm.
Is
I
that?
actually thought that lab was pretty fun.
Oh, it's a good one. I hope
Hmm.
it's interesting the on campus version of it. We have like the whole class trooping up and down the stairs together, waving meter sticks around, wielding stopwatches and stuff. But
Yeah.
hopefully it's fun. And lab classes are kind of meant to be, do something a little different besides just sit in your desk all day. So they
Yeah.
all right. Good stuff. Any other things that you want to clarified or had any questions about?
I do. So at the very bottom of the lab, there was question 12. Um,
And is that the Archimedes lab or the previous one?
still the horsepower one.
Okay.
Um, energy, so the question, I feel like I did everything right, and then when the question came up, it said, how many times larger is the food energy value you calculated than energy needed to climb the tower?
Mm-hmm.
And I think I divided energy to raise person. The energy needed to raise the person through the height I calculated. I think I divided that with the food energy in unit of joules. And I got 9.25.
All right. So I don't have the exact numbers right in front of me, but I do know that that is ballpark that you
Okay.
literally could go up the building 9 times. And I think I've already seen it a little bit of conversation in the forum that people are like, well, how much energy will you really use? And so in like if you look at physiology, which a lot of you guys are going into the health sciences. So yes, like your energy, like the human body is not capable of just taking food energy and converting it straight into levitation up the
Hmm.
building, which mathematically that's what we're doing. We're looking straight at the height energy that we're doing. but it still takes some energy to run your metabolism, and it takes some energy to actually do the walking, right? Like walking just the horizontal distance of the stairs takes energy too, right? And we're only calculating
Right.
the vertical distance. So in real life, as a caveat, and every time we make a calculation, we need to judge how well it represents real life. In real life, that would be the bare minimum energy that you absolutely know that your body has to put out. And then your energy of your metabolism and your energy of your horizontal travel and stuff would be on top of that. But
Okay.
they just kind of wanted a ballpark. If you could physically convert the energy from your food straight directly into vertical levitation of your body, that's how tall you could get from that much food energy.
Okay. Um, so with that one, you can't, I mean, I guess you can, but climb a flight of stairs or the tower 9.25 times. And that was confusing when I was also thinking about rounding. Like, should I have rounded to 9 or should I have rounded to 10 or just leave it at 9.25?
Yeah, so I think that 9 is the number of actual total times that you can climb up the entire building.
Mm-hmm.
So I think they have you do it in flights of stairs first. Am I remembering right?
That's the very last
Oh,
question.
okay. So you multiply. So this is the number of times that you can climb up the tower. So yes. So what they're saying is if you were just using that energy from that food alone, it would get you up the tower 9 and a bit times. And
Okay.
that bit is fine to represent because, that's that extra little energy that's in the food.
Okay.
And technically, you could stop there on the stairs and take the elevator back home or, whatever. We don't really explain the rest of the story, but
Okay,
yeah.
well,
And
that makes me feel better.
well, good. And the logic there is the same as the logic when we were talking about the other lab. If you're doing calculations involving mostly multiplication and division, then however many decimal places you've got, and that includes all place value in your numbers,
Hmm.
that persists. So if all of your inputs, all of your data that you collected, all the numbers you have 3 digits in them, and you multiply and divide and come up with some calculation, then at the end you would report 3 digits. And that's how you know like when the proper place to round is.
Okay, perfect. Thank you.
Well, thank you. I hope that makes things a little bit easier and more
It
straightforward.
does. It does. I have done so bad in school, like when I first started, and now I'm like so determined to get A's in all my classes.
Well,
I'm
good
really
for
trying.
you.
Yeah.
Good
And you
for
make
you.
it very helpful. Thank you so much.
Oh, great. I appreciate, it's nice to be able to make a difference if that's what we hope for.
Yeah. Um,
All right. Is there anything else that we'd like to go over
I wish I had read the Archimedes lab have some
on just
that
questions?
stuff.
But basically the idea with that, I just got another Zoom quit message. Are you still there?
I'm still here.
Okay, I don't know why Zoom keeps telling me it's quitting, but it's not as far as I know. So the principle with Archimedes' principle is when you submerge an object in water, the buoyant force, meaning the force that the water puts on the object, is equal to the weight of the displaced fluid. So that's the big secret with
Mm-hmm.
Archimedes. I'll just delete that real quick. So if we have, if I can get a pencil back, we have a little vessel and it's full of fluid. Normally, the force on an object, and let's just assume we're hanging it from a hook or a string or something. So we
Mm-hmm.
have a tension going up and we have gravity going down. And kind of one of the physics principles is this is free body diagrams. I don't know if you guys have talked about that in lecture specifically, um, but you
I don't.
draw the object and all the forces. Sorry, what were you saying?
I was just gonna say I don't think we have.
Okay, so you know that you have a force pulling up because the object's on a string, and you know you have the force of gravity pulling down, which is equal to mass times the gravitational constant.
Mm-hmm.
So in this situation, and this is all of the forces that are on your object, just when it sits hanging there in the air. Well, in this case, that you know that your T and mg are equal, right? Because otherwise there would be, have you seen this before? the sum of all forces equals to ma. Like that's kind of, you guys have done that in lecture, right?
Uh,
Or sometimes it's just F equals ma, but what it means is the net force.
okay.
Okay, so this is like basic physics concept. Like we have that equation. We know that this means the sum of all forces. This is Greek letter sigma right here. It means sum.
Are you writing on the whiteboard again?
Yeah, can you not see it?
I still just see it's like very zoomed in, so I only see 186 watt. Oh, okay, now I see a little glass of water.
Okay, let
That's all
me,
I see.
because this, all right, it says it muted. Oh dear. All right, so are you still there?
Yes.
Okay, I'm gonna restart the drawing app. And I'm going to share the screen again. Oh, okay. I think I know what happened. I'm going to put this on a different monitor and then reshare it, and hopefully it will behave a little bit better if I do that.
Don't you just love technology?
Yeah, well, what's peculiar is that this is really routine. I've done this many times, and this is the first time I've ever had this sort of thing go on.
Hmm.
Okay. All right. Can you see that now?
Oh, yes.
Okay, so we have a little cup of water. We have, can you see my pencil when I'm not actually drawing?
Mm-hmm.
Okay, great. So this is a general object hanging in the air. There's a tension going up because it's hanging on a hook or a string or something, and there's gravity pulling down. And that's kind of a physics principle. You call it a free body diagram. You draw your object that you care about and all the forces on it. And the way you make sure you have all the forces is if it's in a gravitational field, like if it's in, on planet Earth, it has gravity. And otherwise, it's got one force for each object touching it. When you get into electricity and magnetism, it's also possible to have other forces, but unless you have something kind of funky like that, you've got gravity and you've got touch forces.
Okay.
And then just this equation over here, the handwriting isn't the best, but sigma F equals to ma, that's the sum of all forces, equals mass times acceleration. So if the object is not accelerating, that means that all the forces are balanced, which means the tension force pointing up and the gravitational force pointing down, one of those would be negative. If we wrote down an equation for them, they would balance each other out and there's no net force. Does that make
Okay.
sense?
Yes.
Okay, so now when you dunk this underwater, this is a little tricky because now that I've put it on the screen, I can't use my stylus anymore, but if we put it under the water, we get one more force. And that's the buoyant force, which is the touch force from the water pointing up right here. So now we have three forces, and we know that the magnitude, just the value of them, the buoyant force plus tension, is equal to the weight of the object. But we also have another principle that we know from just knowing about buoyant force, and that is that touch force from the water is going to be equal to the mass of the displaced water. So if this little block just happened to be like a tenth of a liter or something, then that buoyant force would be exactly equal to the mass of a tenth of a liter of water.
Okay.
So that is like basically the physics principle you're trying to learn. And then when you do the lab, um, you're actually doing multiple different things. And what happens if it's not water? What happens if it's something else? Well, it would be the mass of that something else of displaced water that's equal to the buoyant force. So basically, you're just doing the math, you're adding up these three different forces, and you're kind of trying to understand what happens. And basically, the lab just kind of walks you through in the simulation, put it in the beaker, put it under the water, and then to do the calculations.
Okay, that doesn't sound too bad.
Yeah, I hope not. We always hope that it's straightforward, and there's always a few things that can be a little bit confusing. Let me check. I know the in-person version of this lab actually has you calculate you actually get three different numbers for the density of the object, which is kind of the final thing that you're calculating.
Mm-hmm.
And I'm just going to look at it really quick because the online version is going to be just a little bit different than what we do in a physical classroom with physical objects. So, okay, and this is a note, just if anybody's listening to this and is not looking at the announcement, I kind of added a little announcement to the place where this pops up that the equations, if you just open them in your browser or like Google Drive, then the equations sometimes aren't visible. But if you actually download the file and actually open it with an Office product, it should be visible.
Okay.
And I might just link a PDF version of that because it isn't displaying the equations quite how they should be displayed. So maybe I will add to that too. But okay, so it walks you through kind of a step-by-step. One of the principles that you need to keep track of when you're doing the light object, there's a sinker on it to make it sink because it's like wood or something and it won't go under the water by itself. And what happens is when you have those three forces that I illustrated, if you weigh it in the water and you weigh it out of the water, the only difference between those two is the buoyant force, right? So if you subtract those two numbers from each other, you get a number from your buoyant force, like it pops right out. You just take those two measurements and you subtract them, and you've got a number for your buoyant force.
Okay.
And so the same thing, the same principle, if it's too light for that, then you hang a sinker off of it, but that sinker is going to have its own weight. But the secret is if you weigh your object in the air, but with the sinker under the surface of the water, and then you weigh it again with the sinker and the object under the surface of the water, when you subtract the two, it cancels out the sinker entirely. So you just get the buoyant force just like you would if there was no sinker there. So that's just kind of a quick trick that they kind of make you figure out by telling you to measure it that way. And then you have a formula. Okay. So yeah, I'm just looking through. It looks like it pretty much walks you step by step, through the process, and has you measure an object, a regular object, an object that's less dense than the fluid, and then you put your object in something that's not water. Okay. So the questions, one of the tricky things, and if I bolded it, it means that somebody or a lot of people made an oops. So numerical example means that you need to actually say from the lab, I got this number and this number, and because these two numbers add or subtract or whatever you find to this number, then that proves the principle. So when it says did your experimental results confirm Archimedes' principle that the buoyant force is equal to the weight of the displaced fluid? So I showed you in the little diagram how if you measure in the water and out of the water, the difference is the buoyant force, right?
Right.
In the lab, you're also supposed to check the weight of the displaced fluid, which has to do with the volume of the object. So you should have two numbers for that, and they should be just about the same. And so that's what you need to do. When it says you give a numerical example, you actually need to put numbers there and show from your results that that principle is true.
Okay.
Okay, and I think that some people asked about impurities. And that's just kind of an average thing. If you start off with aluminum, which is what the 2.7 that they have you start off with, if you have something, for example, like iron, that's like dense, it's like 8 plus, then if you have a little bit of iron in your aluminum, it's going to raise the density, right? So if you have a dramatically different number than 2.7, and you're expecting 2.7 because you know it's aluminum, you know that something is wrong. If you're confident in your procedure and you don't think that what's wrong is that you measured it wrong, then you would suggest, hey, the block is polluted with something. And if it's more than 2.7, it's polluted with something, the impurities are greater density than the aluminum. And if it's less than 2.7, it's less dense than the aluminum.
Okay.
So I think that the question, they're just like, well, what would the impurities do? So you need to actually discuss that a little bit, say something that you know about the number that you get. If there's impurities, what would happen to that number and what conclusion would you make from it? And that's
Okay.
number 3, how would the presence of impurities change the calculated density? Okay. So it should be, not too scary. Hopefully all those little hints make good sense.
They do. They are so helpful.
Oh, yay. I'm glad. Is there anything else that questions you'd like to ask, things you'd like to discuss?
I think I'm good.
Okay. It's kind of funny. Normally we also have, a small group in the Zoom meetings. You did get the note that I do try to post these afterwards, right?
Yes.
Okay. So it will take a little while to process. I'll put it on YouTube and that will take a little more time to process, but it should be available in the on the site pretty quick.
Alrighty.
All right. Well, thank you very much. Hopefully that makes it a little more straightforward.
Yes, thank you.
Oh, and one other note. Normally I make a rule, just because there are multiple students in the chat and things, that if you want participation credit for being in the Zoom, then you need to get into the chat and actually write your name down and say what your question was. But since you're the only one that's here today, um, I won't make that an official requirement, but just to be
Okay.
aware for next time.
Okay.
Okay. And I'm not seeing your name anymore, but it was Brooke, right?
Yes, ma'am.
Oh, hey, there's another participant here that I'm just barely seeing. Hannah,
Hey,
did you have any? You're muted, but
can
did
you
you
hear me?
have anything you wanted to say?
It was just for the next lab, the big response form.
Okay. Well, go ahead. What's the question?
So it's all the way over to where to go? 19 and 22. It's when the two students are discussing waveforms and things like that. I'm struggling with what is going to be considered redder because I know that majority of those graphs are showing stars that are going to have at least some blue light. So
Mm-hmm.
I'm confused as to how to kind of answer that correctly, if that makes
Okay.
sense.
So can you read the question as it's written?
Yes. Okay. So it's a little lengthy. Two students are discussing their answers to question 18. Student 1, star E, looks redder because it's giving off more red light than star F. Student 2 disagrees, saying you're ignoring how much blue light star E gives off. Star E gives off more blue light than red light, so it looks bluish. Star F gives off more red than blue, so it looks reddish. That's why star F looks redder than star E. And so then it asks, are you agreeing or are you disagreeing with either or both students? Explain your reasoning.
Okay. So the principle to understand here, and we don't have the diagrams in front, and just be aware with those star E and star F, there's like 3 different diagrams. You need to make sure that you're looking at the right one and you've got figured out which line is which. But they all are a curve with a peak at a certain frequency, but some amount of value at the other frequencies. Now, the principle is that each individual star looks the color that's close to the peak. So if you have a star that's got a big peak in the red and you've got another star that's got a peak in the blue, and I think one of the common things, I'm not exactly sure this is the one, but usually there's more energy is towards the blue end. So oftentimes the bigger peaks are in the blue area, And then the red star is kind of got a lower peak, but it's over in the red end of the scale. Now, that red star is going to look red regardless. Like, it doesn't really care what color the other star is. The blue star is going to look blue regardless, and it's where the peak is. Now, that blue star, though, because it has such a monstrous amount of energy in it, it has energy at all different frequencies. And if it has a really high peak, it can end up with more red energy than the red star. But because that whole star is putting off energy in all the different colors, you're still going to perceive that star as blue because it's got more blue than it's got anything else.
Got it. Okay.
So it's allowed to have more red energy than the red star, just as long as it's got more blue energy than that, whatever it is.
And so just to clarify, the color is associated with energy?
Yeah, the color is associated with the peak output. So those graphs, they down at the bottom, they have ROY, they kind of have the rainbow colors to kind of show you where the different colors are. And then they have a height of the curve that represents how much energy is in that color.
Okay.
But when you look at the basic equations that you're looking at, the wavelength, which is the same thing as the color, the wavelength depends on how much total energy the wavelength depends on the temperature. So a high temperature star is going to have a lower wavelength. So you have like two equations that kind of nail things down, but you can also have energy from that, or you can have energy just because the star is huge. And so the first, you started the lab, right?
Yes, I'm done with everything except for 19.
Okay, great. So those first few questions are actually about like spaghetti on a burner. And
Right.
is trying to get you to figure out that you can get energy by turning the burner up or by having a bigger burner to begin with.
Mm-hmm.
And stars work the same way.
Okay.
But you can kind of pin down the energy part by the wavelength because a hotter star changes color. So basically it's saying, if you're on Earth with a telescope and you can't stick a thermometer in that star, well, what can you figure out about it? Well, you can figure out like the temperature because you can look at the color. And then once you know that, you can kind of figure out and compare the various sizes.
Gotcha. Okay. And so when you're asking for explaining my reasoning with disagreeing with those students, would I be using an equation, or are you just wanting us to kind of explain?
So probably the easiest way to just efficiently get the question answered is to figure out, I mean, one of them's right. At least one student out of every pair of students says something that's wrong. It's just not true.
Right.
So the easiest way to answer it is to say, this is what the person said that wasn't true. And this is what is true. If you say that, that's enough to answer the question. So you've got to figure out like what little mistake of logic they made when they made their statements.
So for 19, just so that way I can get my bearings, the student in student 2 is saying that star E gives off more blue light than red light, so it looks bluish. So that would be correct because it's hotter. That's why it's showing that blue color.
Yeah. Let me open the lab. I'm going to have to actually consult with the diagrams before I like say anything specific. Oh, and just a note, it looks to me like Zoom is counting down on us. So we've got less than a minute left, so just log straight back in at the same link when we get interrupted. In fact, I might just let that happen